Beneath these leaves, inside every living cell, and coursing through the soil beneath our feet lies technology so advanced it makes our most sophisticated computers look primitive. This isn't science fiction. This is nature's bioelectronic mastery, and it's about to change everything we thought we knew about technology. In this single cell, more calculations are being performed every second than in our most advanced supercomputers, and it's doing it with practically zero energy waste at room temperature while repairing itself. For decades, we've built our electronic world on foundations of silicon and metal, celebrating achievements like nanometer-scale transistors and quantum computers that operate at near absolute zero. But nature has been quietly running quantum computations at room temperature, storing data in DNA with atomic precision, and processing information through living networks that span entire continents. Today, we're witnessing a revolution as scientists and engineers finally begin to unlock nature's secrets. From Harvard to MIT, from IBM to Microsoft, the race is on to understand and harness nature's electronic genius. In 2023, researchers at MIT's Media Lab achieved something remarkable. They created a working computer circuit using living bacteria, not just a biological system that mimicked computing actual computation performed by living organisms, more energy efficient than silicon and completely self-repairing. Meanwhile, IBM unveiled a neural processor inspired by how fungi networks process information in forest ecosystems. The result? A chip that consumed less than 1,000th the power of traditional processors while handling complex pattern recognition tasks that usually require massive data centers. Nature's mastery of electronics operates on three fundamental levels. 1. Quantum processing. Every leaf on Earth runs quantum calculations to capture sunlight with near-perfect efficiency. 2. Molecular computing, DNA stores and processes information at the atomic scale with zero errors. 3. Network intelligence. Living systems create vast information-sharing networks that optimize themselves automatically. At Harvard's Weiss Institute, researchers have developed self-healing electronic materials based on principles observed in plant growth. These materials can repair damage automatically, using minimal energy and readily available materials. At Microsoft Research, scientists have successfully stored and retrieved digital data using DNA molecules. The implications are staggering. A single gram of DNA can store all of humanity's digital data, every website, movie, and song ever created, all in a storage medium the size of a sugar cube. But to understand why this biological mastery matters, we need to look at three critical challenges facing modern technology. 1. Energy consumption. Data centers now consume more electricity than many countries. 2. Heat generation. Our best processors waste most of their energy as heat. 3. Environmental impact. Electronic waste is becoming a global crisis. Nature has already solved these problems. 1. Energy efficiency. Biological systems operate at the limits of thermodynamic efficiency. 2. Heat management. Natural computation produces virtually no waste heat. 3. Sustainability. Living systems recycle everything, creating zero waste. Take quantum computing. While we struggle to maintain quantum states for microseconds in ultra-cold laboratories, plants are performing quantum computations every moment of every day at room temperature. How? The secret lies in how plants handle quantum coherence. When sunlight strikes a leaf, the energy is transported through the cell using quantum superposition, essentially taking all possible paths simultaneously to find the most efficient route. This process is so efficient it approaches the theoretical limits of physics, or consider how nature handles information processing. The human brain, using less power than a light bulb, outperforms supercomputers in tasks like pattern recognition and adaptive learning. But it's not just human brains. Even simple soil bacteria demonstrate computational capabilities that put our best AI systems to shame. The implications for technology are revolutionary. Instead of forcing electrons through fixed silicon pathways, we're learning to create flexible, adaptive circuits that mirror biological systems. The results are already transforming industries. 1. Medical technology, living sensors that detect disease, self-healing medical implants, biological computers for drug discovery. 2. Environmental monitoring, living sensors for pollution detection, self-powered environmental monitors, adaptive response systems. 3. Data storage, DNA-based archives, molecular memory systems, self-replicating data storage. 4. Computing, quantum biological processors, neural network computers, living calculation systems. But perhaps the most exciting developments are happening at the intersection of biological and digital systems. Researchers are creating hybrid technologies that combine the best of both worlds. 1. Biodigital interfaces, living sensors connected to digital systems, biological processing with electronic output, hybrid computation systems. 2. Adaptive materials, self-healing electronic components, living materials that compute, biologically active surfaces. 3. Network systems, natural digital communication networks, hybrid information processing, distributed intelligence systems. The potential applications are limited only by our imagination. Cities that think and adapt like living organisms, computers that grow and heal themselves, energy systems that mimic photosynthesis, materials that evolve to meet new challenges. But perhaps the most important aspect of this revolution is its potential to transform our relationship with technology itself. Instead of creating systems that fight against nature, we're learning to work with nature's proven solutions. The numbers tell a compelling story. Energy efficiency. Bio-inspired systems use up to 99% less power. Computation speed. Natural algorithms solve complex problems exponentially faster. Reliability. Biological systems show near-perfect error correction. Sustainability. Zero waste through complete material recycling. Current research is focusing on 5 key areas. 1. Quantum biology, room temperature quantum effects, natural quantum computation, quantum-enhanced sensing. 2. Molecular computing, DNA-based processing, protein-based memory, chemical computation. 3. Neural networks, brain-inspired computing, natural learning systems, adaptive processing. 4. Living materials, self-healing electronics, adaptive components, biological interfaces. 5. Hybrid systems, biodigital integration, natural-artificial interfaces, combined processing systems. As we look to the future, the bioelectronic revolution promises to transform every aspect of technology. Computing will become more like thinking, materials will heal and adapt, networks will grow and evolve, energy systems will approach natural efficiency. The solutions to our greatest technological challenges have been operating in nature for billions of years. As we finally begin to understand and implement these solutions, we're not just creating better technology. We're learning to work in harmony with the most sophisticated systems ever developed. The bioelectronic revolution isn't just another step in technological evolution. It's a fundamental transformation in how we think about and create technology. By learning from nature's billions of years of development, we're opening the door to possibilities we never imagined possible. The future of technology isn't in fighting against nature, it's in learning from nature's genius, and that future is already beginning to unfold.